Hello everybody, welcome to the final project presentation of 5330 Pattern Recognition in Computer Vision. Our project is titled as Comparative Analysis of Optical Flow Techniques, Classical Computer Vision versus Deep Learning Approach. And our team members are Arun, Tejaswini, Hardik and myself Francis. Moving to the introduction of our project, what is optical flow? Optical flow is nothing but the velocity field of motion of data at every pixel. This provides us with an approximation of how objects are moving within a frame. Generally, there are two major types of optical flows. The first one is sparse optical flow and the second one is dense optical flow. In the first method, we usually track some of the major features like the edges and corners of the frame, and some of the methods that we use to implement this method is Lucas-Kanade. And coming to the second approach, that is the dense optical flow, here we track every single pixel of the entire frame. And some of the approaches that we use are Farneback and FlowNet. In related works, the Farneback algorithm is a classical computer vision approach that estimates the motion of a pixel in an image sequence. The algorithm works by first creating an image pyramid where each level of the pyramid is downsampled version of the previous level. The algorithm then estimates the motion of the pixel in each level of the pyramid, starting from the lowest level and working its way up to the highest level. The motion data from each level of the pyramid is then merged to produce the final optical flow field. Coming to the FlowNet, it is a CNN model for optical flow estimation. It consists of two branches. The first branch processes the first input image to extract the features. The second branch processes the second input image to extract the features. The features in both the branches are then matched to each other using the correlation layer. The estimated optical flow field is computed from the correlation map. The refined version of this network is used to improve the accuracy of optical flow field. In FlowNet2, the authors have further improved the accuracy and efficiency compared to FlowNet. FlowNet2 uses two-stage training process. The first stage, the network is trained on simple dataset such as flying chair. In the second stage, the network is fine-tuned on more complex datasets such as Sintel. The FlowNet2 uses an iterative architecture of multiple networks, which means the output of one network is used as an input to the next network. This helps the network to learn more complex relationships between the two images. To improve the accuracy of the model displacement, it uses techniques such as modifying the network architecture and fusing the output from the network trained on different displacement datasets.
The scope of our project involves implementation of a classical method and a deep learning based method for optical flow estimation. We implemented the Farneback method as representative of classical methods and FlowNet2 as representative of deep learning based methods. We used MPI Sintel dataset, which is derived from an open source 3D animated short film for the evaluation of optical flow. MPI Sintel was our choice since it has ground truth, which makes it suitable for evaluating the performance of optical flow algorithms. It also contains a wide variety of motion types, including long-range motion and motion blur. The performance comparison of Farneback and FlowNet2 algorithms is done based on performance matrices like L1 error, average endpoint error, and average angular error, which are commonly used matrices to measure accuracy of optical flow estimation. L1 error is the average of absolute differences between estimated optical flow and ground truth optical flow. Average endpoint error is the average of Euclidean distances between the estimated flow and the ground truth optical flow, whereas average angular error is the average of angles between estimated optical flow and the ground truth optical flow. We implemented phase tracking as an application of optical flow. This application detects a phase using Haar cascade classifier on the first frame and predicts the bounding box in the next frame by estimating optical flow inside the first bounding box. The bounding box detected by Haar cascade classifier on all the frames is taken as the ground truth, and the percentage of overlap between box that tracks optical flow and the box tracking phase using Haar cascade classifier will give us a measure of performance of the designed application. We also implemented optical flow for velocity estimation and the movement direction of the detected phases. The comparison results and the demonstration videos will be displayed later in the video.
Yeah, so as we explained, we used MBA's Intel Flow dataset for training and testing the network. We used 744 frames and its equivalent flow outputs as training data, and 320 frames and its equivalent flow as testing data. Training is completely done on Google Colab. However, even after 60 epochs, losses were not reducing much, as shown in the figure here. But the pre-trained weights provided by the authors were already giving us good results. Hence, we chose to use that for the further analysis. Training parameters used for the experiments are shown in the table here. For comparison, we have shown 2 frames from Ali1 category of the dataset. It is clear that the FlowNet 2.0 is giving better results. The white patches in the output from Farneback algorithm might be due to the uniform color within the object. Because if the images have uniform color, there might not be enough variation in the pixel intensities to accurately estimate the motion between the frames. Here is a demo of results on the Ali1 category from MBA's Intel dataset. The mean values of the performance metrics are provided in this table here. As expected, FlowNet 2.0 results are much better than that of the Farneback algorithm. The L1 error, average endpoint error, average angular error of Farneback algorithm results are much higher compared to that of the FlowNet 2.0 results. This might be due to the white patches in the Farneback results which we discussed earlier. The endpoint error obtained for the considered dataset in our experiment is better than the values claimed by the authors. This might be due to the decreased number of test data we consider for our experiment.
As explained in the scope of the project, we have used optical flow to track the phase. This has been implemented in both approaches. The video is first processed by adding a Gaussian blur to prevent the effects of noise. After the optical flow is generated, the mean flow in the region of interest is used for tracking. At the same time, the velocity and the movement direction is also calculated in the same region of interest and is displayed on the output window. We have performed phase tracking using optical flow. The green box tracks the phase only using the optical flow. The red box uses the Haar cascade classifier to track the phase. It can be seen that the accuracy of the deep learning model is much better by seeing the intersection of both the boxes. The intersection between the green and the red boxes gives us a performance metric which we then use to compare the performance of the classical computer vision approach and the deep learning approach. Basically, this means that higher the intersection, the more accurate the model is. On the left side, we can see the object moving through the region of interest. The velocity and the movement direction is calculated in this region of interest. On the right side, you can see how the optical flow field changes when the object moves. This is the optical flow field generated from the FlowNet2 deep learning model. We have also created a UI with which we can control the step size, which is the number of flow points, and also reset the region of interest back to the phase on the click of a button. This is a demo of our UI. Sometimes the optical flow track box does not track well due to its inefficiencies. When we click the Reset ROI button, the region of interest automatically snaps back to the ground truth. We also have a slider on the top that can be varied from 10 to 64. This changes the step size. with 64 reducing the number of flow points and 10 increasing the number of flow points. Thank you for this opportunity to present our project.